Welcome to this lecture in the ongoing series of lectures on real analysis. Today we'll be looking at a very important concept of Cauchy sequences, and let us quickly recap what we did the last time. So last time we discussed the notion of a monotone sequence. A monotone sequence is a sequence x1, x2, x3 of real numbers such that either they are in increasing order or in decreasing order. Or in decreasing order. So decreasing means this. So any such sequence is called a monotone sequence, and if they are in increasing order, then we call it a monotonically increasing sequence, or if it is decreasing order, then it's a monotonically decreasing sequence. Alright, and then we showed that every real sequence has a monotone subsequence. Very interesting and important fact. Using that fact, or before that, we showed that every bounded monotone sequence is convergent, because we can just take the supremum or infimum of that sequence according to whether or not it is increasing or decreasing, and that point, the supremum or the infimum, is the limit of that sequence, which is easy to show. Alright, and using these two facts, we can prove the fact that every bounded sequence has a convergent subsequence, because given a bounded sequence, first we can extract a monotone subsequence, which will already be bounded because it is a subsequence of a bounded sequence. And once we have that, then we use this result to show that it has a point of convergence. So every bounded sequence has a convergent subsequence, and this result is known as Bolzano-Weierstrass property. Alright, these are the problems for this time. And now let us get on with the material of this lecture. So a sequence xn in R is called a Cauchy sequence if for all epsilon greater than 0 there exists some positive integer n such that whenever m comma n exceeds that positive integer, we have the difference between the corresponding elements of the sequence is bounded by epsilon. So after a large enough time, n, the points of the sequence, all of them are pairwise at least epsilon close, or rather I should say at most epsilon close. Right, so we have x1, maybe so x1, x2, x3, whatever, but after some n points of the sequence, wherever they are, we don't care. After that, all of them will be within an epsilon distance of each other. Alright, so basically the intuition is that a Cauchy sequence is a sequence where points come arbitrarily close to each other and they stay close to each other in some sense. I mean, how else do I say it? I don't know, but anyway, I think it is clear from the definition what is the idea behind this. So that's the definition of a Cauchy sequence. Alright, and let us, one way to understand a concept is to look at the theorems around that concept. That's one way, although intuitively it is, I would say, already clear what the concept is. Anyway, so every Cauchy sequence is bounded. Again, this is very simple. So we have, let me first give the intuition. So what we have is, we are given a Cauchy sequence, x1, x2, x3. So the way I am drawing it, it looks like a monotone sequence, but it doesn't have to be. X could be here, x7 could be here. But what this says is that after some large enough n, let's say after xn, every other point is within an epsilon of xn. So all the other points of the sequence are in this interval of length 2 epsilon. Alright, so that part, if you forget about the first capital N things, then all the other things are of course bounded. They are all here. And since the first few things are just finitely many, we will obtain a global upper bound on the size of the magnitude of any element of the sequence. So that's basically the proof, and let me do it in full detail. So let xn be a Cauchy sequence let n be a natural number such that this happens. So this is immediately from the definition of Cauchy sequence. Such a capital N exists. So instead of epsilon, okay, sorry, I shouldn't say. So instead of epsilon, I can put a 1 here. So I choose the epsilon to be equal to 1. Right? In this definition, since this is for all epsilon, this is also true for epsilon equals 1. And so for epsilon equals 1, there is some n for which blah happens. And this is that blah. Okay? So thus in particular, therefore, xn minus x capital N is less than 1 for all n greater than equal to n. So we just instantiated this with little m equals capital N. So if you write capital N here, and that becomes this. Right? Okay. So this implies that xn absolute value is at most 1 plus absolute value of x sub capital N, again for all. Okay, and this implies that mod xn is at most maximum of these things. Now this is for all n greater than equal to 1, because that is the reason we have put them here. So very simple implication, and I hope the proof is clear. Basically this is the execution of the intuition that we alluded to earlier. Okay, so every Cauchy sequence is bounded, and now we'll show that. So fine, so since every Cauchy sequence is bounded, we see that every Cauchy sequence is a convergent subsequence, because every bounded sequence is a convergent subsequence. Alright, but the following lemma says something interesting. So it says that if a Cauchy sequence has a convergent subsequence, then the Cauchy sequence itself converges, and in fact it converges to the same limit, which is the limit of the convergent subsequence. And that part is obvious, but this part is a little bit, it takes a little bit of a proof. Again, this is not very hard. Okay, so this property is not true. If you drop this Cauchy hypothesis, then it is not true. There you can find sequences which have convergent subsequences, but the sequences themselves don't converge. So for instance, if you take xn is equal to minus 1 to the n, then this oscillates minus 1 1 minus 1 1 minus 1 1. So of course it has a convergent subsequence, but the whole thing itself does not converge to anything. So the Cauchy hypothesis is important. Okay, so we start with a Cauchy sequence which has a convergent subsequence. Let xn be a Cauchy sequence. And let this be a convergent subsequence. Okay, and let's say x equals the limit of this guy, and we'll show that x is actually the limit of xn itself. Okay, So let epsilon greater than 0 be arbitrary. By the fact that we have a Cauchy sequence, by the fact that we have that this is a convergent sequence converging to the point x, there is some k such that whenever little k exceeds that capital K, we have this inequality immediate from the definition of convergence. Alright, and now since xn is Cauchy, since this is Cauchy, there is some n in natural numbers such that the difference between any two points of the sequence corresponding to indices exceeding capital N is at most epsilon by 2. So this is for all right. So since the difference becomes as small as we want after a long enough time, the as small as we want we have chosen to be epsilon by 2. So we have used that. Alright. So now, so from here we have to say a few words, but okay. So saying them probably makes it more complicated than it has to be, but what can I do? So let k prime be let k prime be greater than or equal to k such that this thing happens, such that this happens for all k greater than or equal to k prime. So why does such a k prime exist? That is simply because this is an increasing sequence, strictly increasing, of natural numbers. So there has to come a point where this thing exceeds a given natural number. So that's that. And we can choose it to be greater than k also. I mean, there comes a point, but that point can be chosen to be greater than a given natural number. So I hope this statement is clear. And thus, so let me mark this guy as 1. This is 1. Okay. And thus, we have whenever m exceeds capital N and little k exceeds k prime, we have xnk minus xm at most epsilon by 2. So what did we do? We used this equation, rather not an equation, this line, where instead of little n we have put n sub k, where k exceeds k prime. So if k exceeds k prime and k exceeds capital N, so this becomes valid, because this is true only when the indices exceed capital N, and that is satisfied because of our choice of k prime. So this is fine. And now let me call this 2 for reference. So from 1 we have xnk minus x is less than epsilon by 2 for all k exceeding k prime. So if k exceeds k prime, then k already exceeds k, because k prime exceeds k. So therefore 1 immediately implies this thing. 1 was true for k exceeding k, little k exceeding capital K, but since capital K prime exceeds capital K, this is in fact a weaker statement than 1, so it is of course true. So we have 2 and 3, but from 2 and 3, if we use triangle inequality, we'll get the desired result. Using 2 and 3, we have, so all we'll do is we'll just add these two inequalities and use the triangle inequality. So what we have is xm minus xnk. This is that plus xnk minus x, which is that less than epsilon by 2 plus epsilon by 2. And when is this valid? This is valid for all k exceeding k prime and m exceeding n. Right? But here we use the triangle inequality. So what that gives us is that, so basically this kind of cancels away, and what we get is xm minus x is less than epsilon for all m exceeding capital N, and that's it, which implies that this limit, which implies that the sequence converges to x. So that's it. But let me just say a few words as to what happened in the proof. This is the formal proof, but this may look like some complicated thing happened. Nothing complicated happened. What is happening is the following. So we have some Cauchy sequence, and what we have is that some subsequence xn1, xn2, and let's say maybe xn3 is here, and since this subsequence is convergent, it kind of starts clustering around its limit point. It becomes closer and closer to its limit point. So let's say this is your capital X to which the subsequence converges. Now at the same time, we know that the given sequence, the original sequence, is Cauchy. So for large indices, the elements in the sequence, they become close to each other. So if you take little k very large, then xn sub k is close to x. At the same time, if you take some little m large, then xm is close to xnk, provided both little k and little m are large. So if xnk is close to x and xm is close to xnk, then xm is also close to x. And this closeness is maintained for all large m. And that is exactly what we did in the proof, except that we had to give the details, and sometimes giving the details only obscures things. So that is the proof. So every Cauchy sequence has this very nice property that if a subsequence of it converges, then the entire sequence converges. However, we'll say a little bit more. So in fact, every Cauchy sequence itself converges. There is no Cauchy sequence which does not converge. And this is a one-line proof. So the point is that, okay, so let's start with the Cauchy sequence. Then this is of course a bounded sequence. We proved that every Cauchy sequence is bounded. Then xn is a bounded sequence. And hence, by Bolzano-Weierstrass, has a convergent subsequence. Because every bounded sequence has a convergent subsequence. And now by the previous lemma, we see that the sequence converges. So every Cauchy sequence converges. So what about the converse? Is it true that every convergent sequence is Cauchy? Yes, it is. So here is the theorem. A sequence is Cauchy if and only if it is convergent. So there is no difference between a Cauchy sequence and a convergent sequence, but the two concepts look somewhat different. The way we defined convergence was one way, and the way we define Cauchy sequence is another way, but the two concepts are equivalent, and that's a very interesting result. So we have already shown that every Cauchy sequence converges. So all we need to show is that every convergent sequence is Cauchy. I could leave this as an exercise, but let me do it. So all we need to show is that let Xn be a convergent sequence. Want to show that Xn is Cauchy. So let epsilon greater than 0 be arbitrary. Then by the fact that the sequence converges, fine. Let me say that X is the limit. Let X be the limit of the sequence. And now by the fact that the sequence converges to X, there exists some natural number such that whenever little n exceeds that chi, we have this. I'll write an epsilon by 2. So, let me also write this, which it is the exact same equation as the above one, but I just use a different index. So what these two things together give us by adding them is that if m and n are greater than or equal to n, then we have this, which by using triangle inequality. Okay, so this looks like a bad, so this has to be read as this whenever that, and this one is an implication from above, so maybe I will remove this and write hence, and hence implies by triangle inequality this, and that gives us that the given sequence is Cauchy. And that is the end of the proof and the lecture. Guess this is all. Let me check. Yeah, this is all. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.